Hello students, this is Gaurav Saxena once again back on the diffraction, and yesterday we have discussed diffraction due to single slit, and now I am going to discuss diffraction due to plane transmission grating. So all the theory which we have discussed on the basis of diffraction due to single slit, it will actually come into the picture of this diffraction due to plane transmission grating. First, let me discuss that what is the plane transmission grating. So grating is an arrangement which consists of a large number of parallel slits. So these parallel slits may be huge in numbers actually. So in the laboratory we use this 15,000 lines per inch in a plane transmission grating. And the concept behind that so many number of lines is very simple, that we want that the size of the slit should be of the order of the wavelength. And the wavelength of light, what we use in a laboratory or in day-to-day life, is actually 10 is to power minus 7 millimeter around. So that is why we will have this kind of arrangement. The grating is the arrangement by which we can compare the slit size with the size of the wavelength of the light, and then the diffraction we may observe. So grating are constructed by ruling some equidistant parallel lines on a transparent material. So such as glass, we sometimes use this glass or a plate, and then with the use of diamond point, we put the parallel lines here by a machine, and these lines, wherever the lines which we rule on the transmission plate, so the lines act like the opaque space. However, the space between the two lines means two opaque space, act still is a transparent space. So that is why wherever the lines are there, that become a opaque space, and the space between two opaque lines is actually still transparent, and which form a slit. And this kind of very large number of lines have been drawn on the plane transmission plate or the glass, and these ruled lines are forming a slit, and that's why we are having an n number of combinations of the slits. This kind of combination is known as plane transmission grating. The spacing, as I told you, between the lines is of the order of wavelength of the light, and then we will be able to see the diffraction of light. This is a very simple theory. Yesterday I have shown this kind of diagram to in front of you, and that contains was only one slit. Now you can see there are the many number of slits which are at equal distance. This again the wavefront W dash which is coming here, and this grating, this is again the lens and the similar kind of screen. This P naught is that the point which is the center point, and P1 or the P dash is the point which is any arbitrary point. Now the thing is that at point P1 there are many number of lights which will come from all these kind of slit. So in future, in next onwards, the next slide, we take this N, capital N number of slits on the grating. To derive the formula of intensity, let us say that E is the width of slit, each slit. Now there is not one slit, there is N number of slits, maybe 15,000 per inch kind of slit. So that E is the width of slit and D is the space between any two slits. So ultimately E plus D will be the space between any two consecutive slits, and this E plus D is known as the grating element. And we will have the monochromatic light here. We incident normally on the grating, and now by Huygens principle, as I told you yesterday's class, that each of the slit now send the secondary wavelength in all possible direction. So this point P naught is the central maxima. As I discussed, this P naught is the central maxima, and then further P1 or maybe any arbitrary point, you can use the intensity distribution. We will later on we'll see that which kind of distribution will look like for the case of gradient. Now we consider secondary waves traveling in the direction inclined, and they reaches to point P1, which is definitely at point P1. All the waves will be different in phases, and because they will be different, they will have some of the path difference. How can we calculate the path difference? That is an issue. To calculate the intensity at P1, so we consider a theory of Fraunhofer diffraction at a single slit. Very similar theory as we have used yesterday. The wavelets processing from all the points in the slit along their direction are equivalent to a single wave of amplitude starting from the middle point of the slit. So this is the formula, alpha equal to pi by lambda into E sine theta. We know this formula. That was the formula which yesterday we used. So if E is the width, D is the slit width, E plus D is the grating element. So a single wave of the amplitude. So we'll have this A is the amplitude. The amplitude of any one wave will be A sine alpha by alpha. The formula which we have derived in the day before yesterday class. So the middle point of the slit, the alpha we can write, this is the pi by lambda into E sine theta. But here since there are n slits and we have the n diffracted wave, so the path difference between any two consecutive slits will be E plus D sine theta. Initially it was E sine theta for the case of single slit. Now it will be E plus D sine theta. So similar to the previous derivation, we can directly write the phase difference will be 2 pi by lambda into E plus D sine theta. Hence, the intensity in a direction can be found by finding a resultant amplitude of n vibration. This is the difference. Now, there was only one slit, but now there is the total number of n slit. So, the previous case, the small a equal to a sine alpha by alpha. Now, small n is equal to capital N. And delta is equal to 2 beta that we have taken. So, this delta 2 pi by lambda into e plus t sine theta, we have mentioned that this is let it is 2 beta. So the only difference is there. The path difference phase difference become 2 beta. Small n becomes capital N. Capital N is a large number of lines, and then this is A sine N. So substitute the equation, we can get R equal to A. This is sine, and this will become now alpha will become this n delta by 2 and delta by 2. Very similar equation. Once you square this equation and you put the value of A from here, so you will get the resultant amplitude R. So small a comes from there. So this is A sine alpha by alpha, and then sine n beta upon sine beta. And to square this one, we will get the intensity at path point P1, and that intensity would be A sine alpha by alpha whole square, sine square n beta upon sine square beta. This term, A sine alpha by alpha square, is the same term which we have discussed or we have derived for the single slit, and this is the term which gives distribution of intensity due to single slit. That term is also known as a diffraction term. Whereas this term sine square n beta, this n contains the number of slits. If you put n equal to 1, so ultimately this term will be cancelled out. So the intensity will become, this term will be cancelled out for n equal to 1, and this term will result you the intensity due to single slit. So this term is actually distribution of intensity as a combined effect of all the slit. This term usually referred as interference term. So in this for formula of intensity, there are the two terms. This is what this term is diffraction term, and the second term is the interference term. Now we look into the intensity distribution, how the intensity distributed over the screen. So to get it, the case first is the principal maxima. Now from this formula, the I equal to this formula, we will consider only this one because this is already has been discussed as single slit. So for this one, I want this I equal to be maximum. That maxima will give me the intensity maximum will give me the principal maxima. So this equation will take a maximum value if sine beta equal to 0. So if I put sine beta equal to 0, so that will give me the beta equal to plus minus n pi. And that plus minus n pi means n can starts from 0, 1, 2, 3, etc. And that comes to be very different from the single slit because now there are not one maxima. There are actually infinite maxima for all these considered value of n. Because for all these value of n, your beta will be 0, and your beta will be 0 will give you sine beta equal to 0. Go back to this point. So the sine beta will be 0. Essentially, this sine n beta will be 0. And this term will give you the possible value of capital N. If you put the value of beta equal to 0, beta equal to pi, beta equal to 2 pi. So ultimately, the intensity for all these maxima will be proportional to capital N square. That is the intensity of maximas. And so this beta equal to plus minus n pi will give you the value of beta where these principal maxima will form. And this is not 1, this is variety of number because this is n is an integer. So we have the variety of maxima, we will have the many number of maxima. They all maxima are referred as principal maxima, and this n equal to 0 corresponds to 0th order principal maxima. Similarly, for n, 1, 2, and 3, etc., we can have the first order principal maxima, second order principal maxima, third order, and so on. This plus minus sign also indicate that there are two principal maxima of the same order lying on the either side of the zeroth order maxima. Later on, I will tell you how this principal maxima will look like. Going towards the minima side, for the minima position, the equation will take the minimum value when the sine beta is not 0, but your sine n beta should be 0. I want this I0, that I will be 0 when my sine n beta will be 0. And this sine n beta will be 0 only when we'll have this n beta equal to plus minus m pi. Now I have differentiated this m because we have used n earlier. So this m pi. Still both of the integers are same. So I put the value of this n beta, I put the value of beta pi by lambda into e plus b sine theta plus minus m. This is the equation which is for the equation for minima. Similarly, this was the equation e plus d sine theta equal to plus minus L. This was the equation for principal maxima. M has all the integer, but this m has m is the value of the integer, and similarly there n is the integer also. Definitely both will not be same, because if suppose I put this m equal to 0, so my m equal to 0 here, if I put m equal to 0, this will result me beta equal to 0. And this equation m equal to 0 will give me the minimum position. But you go back here, my beta equal to 0 comes here from this first value, and that will give me principal maxima. And both maxima and minima cannot lie at the same place. That is why we cannot choose this value m equal to 0. So m can have all the value but except this m equal to 0. Moreover, if you move further, you can choose m equal to 1, m equal to 2, m equal to 3, and so on. But one time it will happen that your this m will be equal to capital N. Then this n and this n will cancel. So we'll have beta equal to plus minus pi. You go back, again beta equal to plus minus pi will give you the first order principal maxima. Again, it means you cannot choose the value m equal to n. Moving further, you can choose n plus 1, n plus 2, n plus 3, n plus 4, etc. But you cannot choose 2n, because beta equal to m equal to 2n will give you beta equal to plus minus 2 pi, and that's plus minus 2 pi, which is the condition for again the principal maxima. Hence, my m cannot have the value 0 and 2n, etc. And because for all these value, the beta will become 0 and we get the principal maxima. Thus, m equal to 1 to n and n minus 1 values are possible. So between 0 and n, there are n minus 1 possible values for which the minima can form. Similarly, between n to 2n, there are again n minus 1 possible values where the minima can form. So you can see that for these value, n equal to 1, or maybe beta equal to 0, beta equal to plus minus pi, plus minus 2 pi, plus minus 3 pi, there are infinite number of principal maxima, and in between any two principal maxima, there are n minus 1 minima. These are the conditions for minima, m equal to 1, 2, 3, n minus 1, then n plus 1, 2n minus 1, and so on. This will give me the minima position which are adjacent to principal maxima. There is another maxima which will be formed, and that definitely will be the maxima between each minima. Because to get the n minus 1 minima, this is alternate pattern between maxima and minima, etc. So we have the principal maxima, infinite principal maxima, and in between two principal maxima, there are n minus 1 minima. But after n minus 1, all the minima, individual minima, there must be some of the maxima. Those maxima are referred as secondary maxima. Those secondary maxima I will tell you in tomorrow's lecture, because it contains derivation, and obviously we will perform. I will also tell you how can we perform the same experiment in the lab by use of the spectrometer. But so far here, I just want to tell you the picture that how this principal maxima and minima will look like, and this is the intensity distribution. Moreover, I will tell this intensity distribution later on tomorrow in the tomorrow class, but you can just go for that this is what n equal to 0. This was a 0th order principal maxima. Similarly, first order principal maxima, second order, third order, and so on. And in between any two principal maxima, there are a variety of n minus 1 minima also. These are the secondary maxima also. The derivation for secondary maxima I will tell in the next lecture. So we have this n minus 1 total minima. And this intensity distribution curve I will explain in the